All right, so now that we've looked at isothermal transformation diagrams and continuous cooling transformation diagrams, I want to look at the general properties of these various steel microstructures that we've looked at over the past few modules. So let's look at strength and ductility, right? So some mechanical properties. And here we have them as a function of composition, so weight percent carbon. But we also see the effects of that has with the percent Fe3C, right? So if we increase the amount of carbon, we increase the amount of Fe3C or cementite. So what these all show is that strength increases with increasing amounts of carbon. So that's going to have increasing amounts of cementite. And ductility has the inverse relationship, where ductility decreases with increasing amounts of carbon. So strength increases, ductility decreases when we increase the amount of carbon, and therefore have more cementite or Fe3C. All right, so that was for weight percent carbon. But now let's look at some of the different microstructures. So here we're showing spheroidite, coarse perlite, and fine perlite. And it still is a function of composition, but the trends I want you to kind of see here is that we have hardness, which can be a measure of tensile strength, and we have ductility. And what we see is that spheroidite has the lowest hardness, and therefore we can extrapolate the lowest strength compared to coarse perlite, compared to fine perlite, right? So fine perlite has the most kind of boundary between ferrite and cementite. And then if we have coarse perlite, the boundaries are thicker, so there's less of them per area, or sorry, per volume. And then spheroidite has those spherical particles, which reduces the surface area. So basically, this is telling us that the boundaries increase strength. So the more boundaries we have, just like grain boundaries, the more we have, and the smaller the grains are, the stronger something is. This is kind of the same philosophy. So fine perlite, coarse perlite, those are stronger than spheroidite because of the increasing amounts of boundaries between the phases. And the inverse relationship holds true too. So ductility, spheroidite is going to have the highest ductility, and then decreasing to coarse perlite and fine perlite. So anything that has the strongest is going to be the least ductility, and vice versa. So strength increases with boundary. So from spheroidite to coarse perlite to fine perlite, and ductility has the inverse relationship. So this is the kind of the summary table that kind of gives you a summary or snapshot of all the things that we've talked about so far. So we've talked about spheroidite, spherical particles of cementite and ferrite, coarse and fine perlite, which is the lamellar structure, the layers of those same phases. We have bainite, which is also the same phases, but very fine particles. And then we have martensite, which is non-equilibrium phase that has these needle-like grains. And then tempered martensite is the equilibrium phases, but in this very small particles based on the diffusion from martensite. So if we kind of go through the list here, you can see that it's ranked in the relative mechanical properties. So the softest and most ductile up top, which is spheroidite, and the strongest and most brittle on bottom, which is martensite. And so this is the relative scale. So martensite at the top, then tempered martensite, which is strong but has a little bit more ductility, and then bainite is the next, and then perlites and spheroidite in those orders. And it all comes from the relative arrangements, and the fact that it's such a non-equilibrium sort of metastable phase is why martensite is the strongest. So you can kind of come to this table for a very kind of ranked order of these mechanical properties and kind of see what the arrangements looks like and what phases they have. So you can see all of them basically are equilibrium except for the martensite phase, metastable phase here.